Deriving Kinematic Equations with Calculus by Ezekiel Ortega. Why I chose this topic. I wanted to find a way to incorporate math in my presentation, and I also wanted to know the why behind the basic kinematic equations. Defining our initial function. The y-axis will be defined as the velocity of the function, and the x-axis will be defined as time. Our function will also be strictly linear, with the general form y equals mx plus b. Since our function is measuring a change in velocity, the slope can be defined as the acceleration. Since b is the initial value of the function, which describes velocity, we can set b equal to vi, or initial velocity. Since our y-axis is defined as the velocity at that point of the function, we can set y equal to vf. And since we defined our x-axis as time, we can make x equal to t. If we substitute in our new variables for our function, we get the first of the kinematic equations. Final velocity equals acceleration times time plus initial velocity. Important concepts. The derivative. The derivative of a function describes the slope of that function at the same x value. For example, the derivative of the graph y equals x is just 1, as the slope of y equals x is 1 at every point on the function. The power rule. The power rule states that the derivative of x to the n equals n times x to the n minus 1. For example, for the derivative of x squared, we can plug 2 into our power rule to get 2 times x to the 2 minus 1. After some simplification, we get 2x, so the derivative of x squared is 2x. An important note about derivatives. Adding a constant to a function does not affect its derivative. We can see this with the two functions y equals x and y equals x plus 2, as the slope of both graphs remains the same regardless of the constant, in this case being 2. The antiderivative. The antiderivative is the inverse of the derivative. The power rule for antiderivatives does the opposite of the power rule for derivatives, adding 1 to the exponent instead of subtracting, and dividing by n instead of multiplying. An important note of integrating is that it is necessary to add c, known as the constant of integration. This is because of the previously mentioned properties of derivatives, where the constant disappears. So doing the inverse must add back some constant. With our new power rule for antiderivatives, let's try taking the antiderivative of x, or x to the 1. Plugging it into the power rule for integration, we get x to the 1 plus 1 divided by 1 plus 1. After some simplification, we get x squared over 2 plus c. As previously explored in our physics class, the slope of a position graph is the final velocity at that point in time. Recall that taking the derivative of a function finds the slope of that function at the same point. We can combine these facts and define the graph of velocity to be the derivative of the graph of position. Inversely, the graph of position is the antiderivative of the graph of velocity. With this in mind, we can find the equation for final position by taking the antiderivative of the equation for final velocity. After using the power rule and doing some simplification, we get xf equals acceleration times time squared over 2 plus vit plus c. Now, as previously mentioned, our new function defines position, and since c will describe the point of the graph at 0 time, it will be defined as our initial position. After making the substitution, we arrive at our second kinematic equation. The most important aspect of the third kinematic equation is the absence of the variable time. So let's try combining the two equations we have so far to get a new equation without time. To eliminate time, we must first solve for it in one of our two equations. Let's use the first one since it's easier. After some algebra, we get the following equation. Now let's plug this into our second equation to eliminate time. So after plugging it in, we expand out all that velocity, we multiply the whole expression by 2a, we simplify all the velocity and we move the 2a times xi to this side, rewrite it and add the vi to that side. This can also be written as delta x. Sources. Derivation of Kinematics equation by Carolina Knowledge Center. You can ask questions now.